Hello everyone, I'm Jinuk Kim. Today I'll present GuidedQuant, a post-training quantization framework for large language models. This is a joint work of SNU, Samsung AI Lab Montreal, and Google. We start with a qualitative demo on Llama 3.3 70 billion instruct model quantized into 2 bits. The prompt asks for a short story about Harry, Ron, and Hermione. On the left, Squeeze LLM collapses into a repetition loop which is highlighted in red. On the right, a GuidedQuant quantized model produces a fluent 6-sentence story with fresh details shown in green. Even at 2 bits, our method preserves coherence and avoids collapse. Let's take a closer look at how this works. Two families dominate today's post-training quantization method for LLMs. Layer-wise output-based methods that minimize hidden state MSE, and diagonal Fisher-based method that weights error by the gradient of the end loss. However, layer-wise output-based PTQ treats every hidden feature equally. This is suboptimal since each hidden feature contributes differently to the end loss. Diagonal Fisher methods first approximate error by second-order Taylor expansion and ignore off-diagonal terms in Fisher information metrics in the objective. However, discarding these off-diagonal terms in Fisher metrics leads to highly inaccurate approximation since these cross-weight interactions are crucial. GuidedQuant bridges the gaps in these two ideas. We propose to optimize the layer-wise output error in the objective, yet scale every hidden state error by its own loss gradient. Algebraically, this yields a block diagonal Fisher approximation, which is much richer than a plain diagonal approximation. If gradients are uniform, our objective collapses to output MSE. If cross-term vanishes, it collapses to diagonal Fisher. So this objective yields a more accurate approximation than both baselines. However, with this change, the Fisher blocks now depend on each output channel, which makes the method infeasible to compute or store these blocks. To address this, we propose to group channels into few clusters and average the Fisher blocks within clusters and use the average Fisher block instead. GuidedQuant can be plugged into any layer-wise PTQ backend method, and it consistently improves state-of-the-art methods in different formats. In weight-only scalar quantization, it lowers perplexity from 23 to 8. In weight-only vector quantization from 6.8 to 6.1. And it further squeezes the state-of-the-art weight and activation quantization performance as well. Regarding the weight-only scalar quantization, we further propose a non-uniform quantization method LNQ, which optimizes a discrete assignment matrix P and the continuous codebook C while minimizing layer-wise output error. LNQ alternates two optimization steps. It alternates between updating the codebook with fixed assignments using closed form solution and updating assignments with fixed codebook via coordinate descent algorithm. The objective drops monotonically and has a convergence proof. LNQ is fully compatible with the GuidedQuant objective. Equipped together, they achieve state-of-the-art performance in the weight-only scalar quantization as well. To conclude, we propose GuidedQuant, which fuses end-loss gradients with the layer-wise quantization objective, and LNQ, which alternates closed-form update for codebook and coordinate descent update for assignment in scalar quantization. The code is open sourced. Scan the QR and try using it. Thank you.